Alright guys, we are back with the final video in chapter 14, and we are transitioning from a discussion about exceptions to Mendel's rules in the second video into a tracking of human traits, which also sometimes do follow Mendelian patterns. Now, it's a lot harder to do genetic testing and research on human beings for various reasons. So it's harder to know more about Mendelian genetics and how they play out in various generations efficiently, like Mendel did and like we saw in some of the previous material. The reason for that is a few reasons. Humans don't make a ton of offspring. Now, when Mendel did these pea plant experiments, he did experiments where he was getting thousands and thousands of offspring that he could look at and take data for. And when you think about scientific data, one of the things that always seems to pop out as a theme is that they wanted to see more and more and more and more data. It's very hard with human beings because some people have no kids, some people have one or two, or maybe one. So you don't get a whole lot of data. Now, there's a lot of people in the world, yes, but the other thing you got to think about is that breeding experiments that you might want to run in a Mendelian genetic study on human beings would be considered unethical. So you have to just let natural matings happen. So it's almost like random mating in some sense. You can't control who's going to mate with who, or what traits are going to be passed on, or what traits might combine, or what traits you might find in the offspring. So breeding experiments are unethical. You're not just going to force people to mate, at least not in this country you aren't, and very hard to get any controlled data. And then generation times for human beings tend to be way too large. For a human being to get to the point where they're going to reproduce another human being is going to be in the neighborhood of anywhere from, unfortunately, 13 years young to 25, 30, 40 years old sometimes. Those are the age ranges where you would see sexually mature females that would allow for babies to be born, and so generation times are just too great. You have to wait too long to actually get the next baby. So Mendelian genetic studies on human beings are difficult. However, basic Mendelian genetics endures as the foundation of human genetics because we do have a lot of traits that follow these basic patterns. So, how do we track these patterns? Well, if we can't do all these breeding experiments and it's not efficient to do so, how do we look at that? We use genetic research. Okay, we use something called a pedigree analysis, and you can study what is called a pedigree analysis, which is basically a genetic family tree, okay? And it describes the interrelationship between parents and children and across generations and who has come into the family and what traits do they have. And inheritance patterns of particular traits can be traced and described using these pedigrees. And so you can predict with some certainty, at least within a family or families, what future offspring might look like, or what certain traits future offspring might possess. And so with these pedigrees, you can use all of the natural statistical analysis tools that we've already talked about. You can use Punnett squares, you can use the multiplication and addition rules of probability, and those will help you figure out the probable chances of specific phenotypes in a population. Okay, and sometimes it is a population. Sometimes a population is so closely related you can look at a population of a small town or small country, and figure out what is the incidence of a certain disease, or what is the incidence of this particular trait. Kind of neat. And so what you see in front of you right here, I keep this picture included with the stock stuff that the book gives us because I find it fascinating that this is looks to be a genetic counselor who has just a giant pedigree. Looks like a giant pedigree she's tracking some kind of traits. I'm not entirely sure which one, but you know, she can figure out the odds that certain children are going to be born with some kind of disease, maybe a genetic disorder, definitely something passed down genetic, okay? You know, nobody's going to put this type of work. I mean, maybe you have somebody who is very bored, is going to put this type of work into figuring out, you know, whether or not you're going to have brown hair or green eyes. People aren't going to put that much work into figuring that out. But, you know, if putting this together means you can understand, you know, whether or not you're going to get sickle cell anemia or cystic fibrosis or something like that, you would want somebody to put that time in and help you figure that out. So. It seems to be a really cool profession. If I'd have known about it when I went into school, I might have done something like that. But a genetic counselor gets to play with this stuff quite a bit in their regular everyday jobs. So, how do we look at a pedigree analysis and decide anything about it, really? It's hard because different pedigrees kind of have different conventions and different rules. There's kind of a stock set of rules that almost all pedigrees share, but even from pedigree to pedigree, you might find different symbols that mean something subtly different. As far as I know, and I haven't done any research, so you can't quote me on it, and if you want to go ahead and prove me wrong, that's fine. I'm happy to be proven wrong because that means I'll get smarter. But I don't think, or I've not seen or researched anything that says there's like a standard normalized way of putting together pedigrees. I don't think there's like a pedigree analysis national board or anything like that where they come to a consensus on the symbols to be used. But a lot of these, if you get a pedigree or if you're making one, there's like a pedigree key, kind of like how you see here, where it'll tell you what the symbols actually mean. And so usually on these pedigrees, what you can know for sure is that a male and a female are going to have specific symbols. The male is almost always a square. I've never seen one where the male's not a square. And the females are almost always the circles, as you can kind of see here. This is the female and this is the male. The individuals who express the trait, okay, are generally shaded in. Okay, so we can see right here, these two express the trait, so they'll be shaded in. I have seen some where that's not the case, and I don't know why, but this is almost always the rule. Like, if you are tracking a certain trait with these pedigrees, the box or the circle are filled in if the person expresses it, okay, whether it be a recessive or dominant trait, either one. I've seen this symbol change. Females or males who are carriers for the allele but do not express it. I've seen it done with like a half-shaded box, which means they don't express it. You can't see it in them, whatever the trait is, but you know for whatever reason that they are a carrier of the gene, that they could pass that on to somebody else. Okay? And then you've got all these other ones here. And then so the lines do mean something as well. When you go down, that indicates that you're on to the next generation. When you go across, that means, or when you have a line that links two people in a pedigree, it means that they're partners. Most oftentimes it means that they will have had kids or made children. Siblings are indicated like this, okay, like this little bracket. Adoption, they can even put adoption on these things. They show symbol here for identical twins and then even fraternal twins. So they have symbols for all these things, and depending on the pedigree that you happen to be looking at, sometimes the symbols can change, unless there is a standardized version of this, which I'm not sure there is. All right, so the first one that you see here is super, super basic. This is a pedigree that tracks the dominant trait known as, I call it butt chin, and I can do that because I got a little one. I'm allowed to say that since I have one. But it's more accurately, more scientifically called a cleft chin, okay? And so the butt chin, or the cleft chin, is inherited through a dominant allele. So if you have the dominant allele, you will have the trait. And you can see here all the people who have it. So it looks like grandpa has it, grandma doesn't. Grandma on this side has it, this grandpa doesn't. And then you could theoretically track this trait's pathway through your family, okay? And you can deduce, okay, based on what this happens to be, what these genotypes happen to be, I could predict what these genotypes possibly could be, okay? Now, it's not as cut and dry as this. This happens to be one that's just been thrown together. But we're going to get practice at figuring out, okay, this person right here has the trait, but how do we know it's heterozygous? Okay, this person, let's say we didn't know what grandma was, her genetics. We didn't know her genotype. We know she expresses it. How would we know whether or not she's big B, small b, or big B, big B? How would we know whether or not she's heterozygous or homozygous dominant? Those are things that the pedigree can help us to figure out, but we have to be thinking critically, and we have to do some logics thinking as well, okay? So the people in this one who are unshaded do not express the trait. I think I forgot to incorporate that into my previous slide. But yeah, you can see here, you can track the inheritance patterns of these things throughout different generations, okay? We can also do this for recessively inherited traits, okay? And I'm not going to say disorder, even though the attached earlobes kind of do look a little bit freaky if you have them. I've got the unattached ones. But this particular pedigree tracks the attached earlobe being the recessive, okay? And so anybody who's got the attached earlobe, as we see right here, would be indicated with the shaded in box, at least in this pedigree. And in this case, we would know for certain that their genotype is small f, because the trait is recessive. And so we know anybody who expresses it automatically is homozygous recessive. Okay? So we can see that traced down through the generations as well. Now, I'm going to take a little bit of time because, you know, we don't use these pedigrees under normal circumstances, like professionally. I don't personally, but you know, genetic counselors are not going to do pedigrees and you're not going to pay a genetic counselor to do a pedigree to see if your children are going to have attached or unattached earlobes. You're going to pay a genetic counselor to tell whether or not your children are going to have recessively or dominantly inherited disorders. So just a brief description of at least one or two of each, right? I think that would be warranted here at least. So there are some recessively inherited, there's a lot of recessively inherited disorders. The one I chose to at least highlight here would be sickle cell anemia. Sickle cell anemia only shows up in individuals who are homozygous with the recessive allele, which means they have to have 2 copies of that recessive allele for sickle cell to actually express this gene, okay? Carriers for sickle cell anemia are heterozygous individuals who carry one recessive allele, but they're phenotypically normal, which means they don't express the debilitating side effects of sickle cell anemia, but they could possibly, because of the nature of the fact that they have a recessive allele, pass that on to their children or possibly grandchildren. Okay? So sickle cell disease caused by the substitution of a single amino acid in a hemoglobin protein in your blood cells, and it's actually quite common. You see it more often than you would think, and there is a reason for that, and we'll talk about the commonality of it and why it happens to still be relatively prolific in the population. We'll talk about that when we get to the evolution chapter. It's actually pretty fascinating. But this is a mutation caused by a mutation, and that mutation causes a recessive copy, a recessive version of that gene, which we can pass on and can eventually cause disease if somebody gets 2 copies of it. Okay, and so the symptoms for this can range anywhere from, you know, some physical weakness and pain to close to paralysis and death. I mean, it's depending on how bad you have it, and it comes in waves. It seems to come and go depending on how badly you have it, and what environment you find yourself in. These episodes can come and go. A lot of time you'll see people who have sickle cell anemia. You'll be able to pick them out of a crowd because they love chewing on ice. You know, I know of a couple people at least that I've seen in this school who have sickle cell, and they always have a cup of ice. There is a reason for it. You'd have to Google it or something, but I for the life of me, I can't remember why. I probably should have researched it before I made the video, but it'd be a good thing for you guys to figure out. But you'll see people with sickle cell eating ice all the time, which is kind of interesting. There are also dominantly inherited disorders, and this kind of goes along with the fact that, you remember I talked about the polydactyl, right? Having 6 fingers is actually dominant compared to recessive. It's kind of along the same lines. You wouldn't think any diseases would be dominantly inherited, or disorders would be dominantly inherited, but in fact they are. And one of the ones that I find rather interesting is called achondroplasia. And achondroplasia is the scientific name of the disorder called dwarfism. We would commonly know it as dwarfism. And people who have a dominant copy of this gene express the dwarf-like features, the small people features that you would see in this picture, okay? And this family is actually quite interesting in terms of, what they're all about, because you see here in the middle are the parents, okay, and they express achondroplasia, which means that they are heterozygous for it, because achondroplasia happens to be lethal when you have 2 dominant copies of the trait. So we know that everybody on the face of the planet who has achondroplasia is heterozygous for that trait, okay? Because by virtue of they're alive and by virtue of the fact that this is dominantly inherited, we know that anybody on the face of the planet that has achondroplasia is heterozygous, and because anybody who would have gotten 2 uppercase M's or 2 dominant alleles would have passed away long before they would have been able to make children. Okay, and so we can kind of see how that works here in this family. Now, the interesting part about this family is that they actually actually have quote-unquote normal-sized children, right? And so this is something I'd like to talk a little bit more about when I see you next in person, okay? Just do a kind of a crash course in achondroplasia and kind of veer off and branch off into a couple of other talks with this. So I look forward to discussing Little People, Big World, and I will talk to you soon.